You're all set.
Okay, very good. So here's what we're going to be talking about. And again, we've got a chapter on starting systems in the reference book, so you can always refer to that. So those are the main topics that we're going to be talking about. And just a quick note here, I may have mentioned this before, but we're not favoring any particular manufacturer or technology. So we try and spread the fame around. So starting systems, you might think this is a rather curious choice because all of you, I'm sure, have started an internal combustion engine within the last 24 hours. So why are we doing this? Well, there are some differences between starting systems on generator sets and starting systems on engines. And this is what we want to explore, because if the generator set doesn't start during an emergency, someone is not going to be happy. And you can probably guess who's going to take the blame for a generator set not starting when it's seriously needed. And that's probably going to be the last technician, the technician's employer, the generator set manufacturer, and anyone else down the line. Someone is going to be really upset that all that money they spent on an emergency or standby generator set was to no purpose. The thing didn't work when it was supposed to. But here's an interesting fact. Read this. That was from Cummins. Okay, here's a question for you guys. What's the number 2 reason why generator sets don't start when they're supposed to? Can anyone take a guess at this? Or not a guess, you may have experience with this. Direct knowledge. What's the answer?
Fuel pump, perhaps?
Okay, that's a good suggestion. It's right up there, but it's not number 2.
Cold weather.
Sorry, say again?
Cold weather.
Possibly. What else?
And the heaters, generator heaters.
Yep, that can cause a failure to start if the engine is too cold. This is something that doesn't apply to generator sets that are used constantly, but for standby and emergency generators, often, and the number 2 reason is actually this. Someone went to work on that generator set and they did the right thing by turning it off before they started working on it. And then when they left the building, they forgot to put it back to the auto position. So it's just not going to run when it's in that position there in the off and reset position. So that's the number 2 reason. Okay. So we're going to delve a little bit into why there is a problem with generating starting systems and what we can do to improve that. Now, the basic system we've got is pretty obvious. You've all seen this. You've got a battery, you've got a starter motor, same as you have in a car, basically. You've got an alternator. On a standby generator set, that's not doing a lot of good other than keeping the belt in tension. And we've got a solid state battery charger that's plugged into the wall. Okay.
One more question.
Yeah, go ahead.
And when the generators get bigger, normally it has a air starters, right? Pneumatic starters.
Oh yeah, many do. That's right. Yeah. I'll mention that just a few slides from here. Okay.
Okay.
Yeah. So, but you're right. Not all generator sets are started electrically. But it's the electrical starting systems that give the most problems. So that's why we're going to be pretty well focused on this. Okay, so we've got a block heater there because a warm engine is going to start much better than a cold engine. Okay, so what are the differences and the causes of failure of these 2 systems? Now, we've got your personal vehicle and a generator set. excuse me for choosing this particular vehicle. It's a Russian-built Lada, and I use this because I know that none of you would have one of these cars. It was basically a piece of junk produced by the Soviet Union. They did say that you could double the value of that car by filling the tank with gasoline. Anyway, so what would you say, we'll all have different opinions on this, is the leading cause of failure on a vehicle? Not on one of those cars, but on your own car. It could be any one of those. Anyone has a
Starting
guess?
system.
Yep, sure. Okay. Anyone have problems with powertrains? That's kind of a unusual one, unless it's a really old vehicle. For me, I got a software problem on my car, and apparently it's going to take about $1,800 to replace a little computer. The car still runs, but I don't have a lot of the bells and whistles that I'm supposed to have. Fuel system sometimes, but I think on a modern car, it's usually the software. I mean, people have their own different experiences. Now, on a generator set, what's going to be the leading cause of failure here? And we've actually got data on this. Well, it's going to be the starting systems, which coincidentally is why we're doing this this module. So, coming back to the question a minute ago, how can an engine be started? Obviously, we've got electric. We just mentioned air starting. So the one end of the starter motor looks exactly the same as this. You've got a pinion here and probably a gear. So compressed air goes in this. I think this one is manufactured by Ingersoll Rand, who does most of these. So these are used in areas where either you have a good supply of compressed air and it really simplifies the system, and simplification makes it more reliable. So it's a good option to have where you have a decent supply of compressed air. What else is there? What other forms of starting a generator set engine can we use? It's all about stored energy, isn't it? So we've got electric starting, we've got air starting. What else could we have?
And crank.
Hand crank? Yep, absolutely. Thank you. What else? I wonder if anyone has heard of hydraulic starting. Again, you've got the same end to it, but you have an accumulation of hydraulic pressure. And at the right moment, you press the button or push a lever, and it will start the motor going and start the engine for you. And then we have hand crank or rope pull. I was doing some pressure washing earlier this morning, and the damn rope broke. So I had to get some more rope and tie that on. And crank for a more serious engine on the lower right there. And there's one other, which is actually a marine application, believe it or not, but lifeboat engines are required to have two completely independent means of starting. So electric starting is going to be one. Hand crank in some cases is available on some engines. The other one is a spring starter. And what you do with a spring starter is, on here there's a little hex. You put a socket there and crank it up. You're winding up the spring. You're storing the energy in that spring. And when you're there, when you've turned it enough, with a little red light in this little hole here. And at that point, you're ready to go, and you can just press the lever and that engine will start. Okay, what else? Any other form of starting any engine? How many of you drive a stick shift? The battery is dead. You can push that engine. The driver will be sitting there with the probably second, maybe the third gear engaged. And when this guy at the back, when your best friend has pushed the car fast enough, then you pop the clutch and the engine should start. If not, you're really pushing his friendship. So that's another option. Anything else? Well, there is another one as well. I don't know if any of you have seen this, but here we've got a this is actually shown in a bulldozer, but I've seen these on generator sets as well, on old Caterpillar. This is a 2-cylinder gasoline engine, and this engine can be fairly easily started. And once you've got it started, you can ease the clutch on here, and it'll start turning the main engine. So there's no electrics involved, and makes it very simple. Apart from the complexity of the first engine, of course. So this is usually referred to as a pony engine.
Is there a such thing as compression starting?
Good question. Yes, there is. There's one system that is actually, I don't have a slide on it on this presentation, but there is a method of starting a rotary aircraft engine where you basically are using a 12-gauge shot. You put that into the breech on the side of the engine, you crank the engine over using the propeller to get the cylinder just past top dead center. And then you close the breech, pop that cartridge. Obviously, there's no bullet in the end of it, but the explosion there will force that piston down and cause the engine to start. Did that answer your question?
Yes, amazing. Thank you.
Okay, I'm sorry I don't have a picture of that. Okay, here's another method of starting a bad misbehaving engine. Starting fluid. This is almost a requirement on some old Detroit diesel engines, the 71 series. I don't know if any of you are familiar with that, but you get the engine cranked over and you spray ether into the air cleaner, and then that'll get it to start. We don't recommend that. The results can be on a regular engine, it can be disastrous. You can get a broken crankshaft, broken connecting rod, and if the engine fires and starts, then that whole thing could come apart and wreck the engine. And what happens here is, oops, let me come back to that. There we go. Right around here, there's been some damage to the piston ring. Part of the piston ring is broken off, and bits and pieces will be grinding themselves along the cylinder wall and on the cylinder head. So the only person that's going to be happy about that is this guy, who's going to be rebuilding the whole engine for you. I like that. I saw that somewhere the other day. A rapid unscheduled disassembly of an engine. In other words, the engine blew up, folks. That's what happened there. But we can turn the English on it and make it sound like an everyday affair. Rapid unscheduled disassembly of an engine. Oh, here we go. I just inserted another slide in there. So here we go, putting a 12-gauge shot into the side of the aircraft engine. And if you want to see it working, you can see the plane being started on that link down there when you get your copy of this presentation. Oh, sorry, we got duplication here. So let's examine the differences between the starting system on a car and the starting system on a generator, and see if we can identify anything that would be a sort of red flag and cause us to have more problems with the generator set. So first of all, let's ask ourselves, how many starts a year do we have with a car? Well, I thought about this for a minute, and I thought maybe if we have 4 starts a day, 7 days a week on average, times 52, that is going to give us 1,500 starts in a year, okay? If you got kids, you can probably double that, right? On the generator set side of it, if it's a standby generator set, it's going to be starting up, sadly, once a week and run for an hour. So we've got the exercise and maybe some extra time, running time, testing time, and emergency time. So we may have 100 starts a year on the generator set. Okay, so that's to the benefit of the generator set, really. Failure to start. Very infrequently. And the thing about a car is that if you have a failure to start, you can usually tell that you've got a battery that's getting flat, and you can do something about it before you're stuck in the boondocks somewhere. And a generator set, failure to start. We've all got our, certainly technicians have got our own experience of this. So I'm going to leave that one alone. Replace a battery on a car every 3 to 5 years, probably. I've been getting at least 5 years out of a battery before I need to replace it. On the generator set, if you're prudent, you will replace that battery on an emergency or standby generator set no more than after 3 years. Number of hours on charge. The average car owner apparently does about 12,000 miles a year. Say the average speed is 30 miles an hour. That means that the battery is on charge during that period, which is about 400 hours. What about a generator set? How long is that on charge if it's a standby or emergency? What's your input on this? Do you remember that first picture we had of a generator set? The different components on there? I said the alternator was pretty useless because we've got a solid state battery charger on there. It's plugged into an outlet. So how many hours a year is that going to be on charge?
Pretty much 24 hours, 365 days a year.
Thank you. Absolutely right. 24/7. There are 8,760 hours in a year, right? It's a useful number to remember. Well, there's a huge difference right there. It's 17 times longer on a generator set than on an automobile. So that is significant. Okay, let's just take a quick look at a wiring diagram here. So here's an automotive starting system, and the only difference between it and our kind of business is that we may have a battery heater where you guys are. You probably won't, but there may be a battery heater around there, around the set, and you'll have a battery charger that's plugged in. Incidentally, the symbol on the let me just get a laser here so I can be more pointed. So this represents a sine wave. So on a wiring diagram, you'll see this showing AC current, and a flat line here shows DC current. So what we're doing with a battery charger is we're taking AC and we're converting it to DC, to 12 volt DC. So the main differences, here are 5 important ones. There's number of hours on charge. Instead of about 400 hours, we've got 8,760 hours on charge. In the car, you're going to get an early warning that the battery is getting weak. On some cars now, you'll actually get a dashboard warning that you've got a low battery. Car manufacturers always make sure that everything that they put on that car is sized and specified and works in every environmental condition that is likely to be encountered by that vehicle. They have an engineering validation process. So they check everything out and make sure the battery is the right size, the alternator is the right size, and everything fits and is all correct and works properly. Does that happen with generator sets? No, it does not. The starting equipment, the critical stuff, the battery charger, the maybe battery heater, and the battery itself is specified by usually the generator set assembler, a distributor, or maybe the engine manufacturer, or a consulting engineer. So there is no engineering study done on its suitability, or very seldom anyway. And that brings us to the fact that it's an open system. Is who chose this system? And I apologize for a minute. We might get a little bit of barking in the background. I hope it doesn't disturb you or distract from what I'm trying to tell you. Well, two dogs making a bit of a noise down there. Okay, I think we're past the worst of it. The other thing which has some significance is a battery heater, and I'll get into that a little bit more. But here's an interesting thing. Looking at this study, the results of this study, the automotive battery has gone from a life of just under 35 months back in the last century, and it's improved up to the fact that you can now get just under 55 months on average out of the battery. On generator sets, it hasn't changed at all. 36 months is generally the max that you're going to get. So there's, and they're the same battery. So what's with that, right? I mean, we take a battery from the auto parts store and we can start a generator set with it. Same one that the cars use, but the life is very different. So there's different types of batteries that we can use. You've got the flooded type, easily recognizable. You've got little plugs on each cell so that you can check the electrolyte and check the specific gravity, top up the electrolyte if necessary. You've got the absorbed glass mat. AGM batteries are a little bit better. It's all enclosed and there's no electrolyte evaporation. So it's all contained within that battery. And you've got a version of this, a spiral. I don't know if any of you have seen this, but and I don't think I've seen one of these actually. But it is another technology that gives you a little bit more of a punch because you've got more cells in the equivalent of more cells in there. And basically the absorbed glass, and the glass refers to fiberglass. So the electrolyte is actually in the fiberglass. And in the case with a spiral, it's a great long mat with the electrolyte embedded in the fiberglass, and then it's all rolled together and connected to each of the others. So batteries are indeed energy storage devices. Here we come back to energy again. Remember that energy can't be destroyed. It can only be converted. You get a certain amount of energy and you convert it into other things. So we're going to be talking about the two most common technologies, which are fairly old technologies actually, lead acid and nickel cadmium batteries. And these are what we see most often on generator sets. We're going to look at the temperature effects on batteries. Some of you already have experience of trying to start a vehicle or an engine when it's cold versus when it's hot. And we'll take a look at some of the newer energy storage technologies, new battery technology that's coming up. So let's go to some basics here. You can't stop that battery's action. It's chemical energy that we're talking about here. The chemistry doesn't stop. You can isolate it with a switch, but you can't stop that chemical reaction that's happening inside the battery. And that has a result that it will self-discharge over time. But fortunately, we can recharge that battery. And here's a diagram of what we're looking at, what we're talking about here. So the lead acid battery, we've got a cathode and an anode, and the electrolyte moves between the two. We've got a separator plate here so that these two don't come in contact with each other. We may have a charger running here and a switch. Each of these cells, this is one cell here, they will develop 2 volts per cell. So clearly we need 6 cells to give us the 12 volts. If we need 24 volts, we put another one in series. So we'll have 12 cells all in series with each other. Now, the nickel cadmium battery, on the other hand, uses a slightly different chemistry. And you can tell the two apart by the fact that the connections between the cells are all external. So you can see them. And the cells on the NiCad battery are 1.2 volts per cell. So we need 10 of them to give us 12 volts. We're going to get into the advantages and disadvantages of each cell. And you know, from prime movers, I like doing that stuff because it gives us a better view of the options that we have, a little bit of education. So let's talk about the performance of a battery when it's cold. The red one, the red line here, is a lead acid battery. And you can see that we got percentage on the vertical scale here and temperature here. And for those of you that are not bilingual, there's your Fahrenheit scale. So at we get 100% performance at about 70 degrees or so. So that's the best point there. And as the temperature decreases down to 32, we're only going to get about 85% of its original capacity. As the temperature goes down to 14, then we're down at 65%. Now, you couple this with the effect on the engine, because that's going to be cold and it's going to be harder to crank. So we may have a real problem here. So there are ways around that problem, but it's important to be aware of the difference here. There's two types of NiCad battery, and you can see that starting off at the same point at 100% capacity, this one here is not affected nearly as severely. You come down to the point of 14 degrees, this one still has a way to go before it drops only down to 70% of its original capacity. And then over here, we got 75% with a different technology. So where you've got really cold temperatures, the NiCad is the solution to lead acid. I did a project in, actually for a military operation in Antarctica. The engine generator set had to be capable of starting after it left on its own without any attention during the winter months. And we had to prove that it could be started at, I think it was minus 45 degrees Celsius. Actually, that temperature doesn't make any difference whether it's Celsius or Fahrenheit. So we had to use an NiCad battery for that application. So that's the effect of the cold temperature. So what can we do to counteract the cold temperature capacity loss on a lead acid battery? Well, the obvious solution, of course, is we can warm it up. We can give it a blanket, give it a heater pad. So what is the effect of high temperatures for a starting battery? Kind of interesting. At 77 degrees in this study, you get about 44 years of life out of the battery, lead acid battery. A NiCad, because of its technology, you're going to get 20 years, no question about it. Increase the temperature to 91 degrees, and that's going to reduce the life of that battery by a half. Only a little bit, from 20 to 16 and a half years with the NiCad. And then at 106 degrees constant temperature, then you can see what happens. Actual mileage may vary. So this is just one study that was done. And looking inside the battery, you can see here, we've got a negative plate, a positive plate. We've got grids, which has a lead, and then we've got a separator. Now, this separator is an interesting little thing here because it's made of polyethylene, and after time, it will decompose. And the thing that causes its decomposition is the amount of time it spends on charge. Now, isn't that we've got this thing on charge all year, for years on end. And eventually this is going to break down. We're going to have, at that point, very little separation between the two plates. And that can cause a catastrophic failure. It will stop working. It'll get very hot, and it may even explode. So but by that time, you hope that someone has realized that the battery is not holding its charge properly, and it may happen fairly slowly with time, and the battery can be disposed of and changed before you have a major catastrophe. So there it is. Now you see those little grids there. They also suffer as well. And with the effect of lead moving on and off these plates, this grid is going to expand. Here's the darker shadow here is the original size, and it's going to expand to about 1.3, 1.5 of its original size. And in doing so, it's going to break some of these, some of this grid. So that's going to cause the battery to fail as well. Here's our lead acid on the left and our nickel cadmiums on the right. You can see the individual cells, and here's an installation that's got a whole bunch of cells. They're heavier, they're bigger, they're more expensive. And let's just look at some of the differences between the two, because like natural gas engines versus diesel engines, we've got a choice here. So the question is, which is going to be better for a particular application? Do we go with a less expensive one, or pay the money and get the more expensive one, in this case, which will be the NiCad? So the advantages of the lead acid battery, let's look at those to start off with. Who tell me, give me an advantage here? Well, several advantages.
The lifetime of the battery, it's generally longer.
Actually, that's not an advantage with the lead acid. It's not going to last as long as the NiCad battery.
How about
Okay.
it's tried and true?
Yep.
Reliability.
Yep, that's right. They're available. They've been available for years. They're in common use, which means they're easy to get, right? You can go to the auto parts store and pick one up. They'll have it right there for you, fully charged, ready to go. What else?
And those are generally cheaper.
Yes, they are. Definitely. Those are the lowest cost. And this is why we see the lead acid batteries all the time on standby generator sets, because many of the standby generator sets are sold on the bid process. Lowest bidder gets the job. Lowest bidder that meets the specification gets the job. So if he can save a few dollars on a battery, they're going to do that, put the cheapest battery on there. So that's one advantage for the bid process. Any other ideas?
Is the power density higher?
Not really. No, I mean the batteries are all have a certain rating to them on amp hours, and so you buy them on that basis. But physically, there's an advantage space-wise with the lead acid. So I think that was your point, and you're correct. Okay. All right. Readily available, low cost, easy installation, easy disposal. Just take it along to your recycling center, and they'll take care of it for you. And easy replacement. Just go and get a fresh one. What about disadvantages of the lead acid?
Safety hazard from the from the acid, and hydrogen generated during charging.
Yep.
So need like ventilation for the room.
Yep, that's important. You don't want to stick your head in there if there's any doubt of that in your enclosure if it's been discharging. Okay.
About electrolyte maintenance.
Yeah, that's something that's got to be checked. If it's the flooded type of lead acid, you do need to check that every so. That should be a regular check item on your maintenance. And a couple of other things. When it's cold, it loses power. When it's hot, you lose mean time to replacement. It'll fail in a hurry without any warning. So you need to replace it at the end of its or closer to the end of its calculated life to avoid a catastrophic failure. And the advantages of the NiCad battery. What would we have there?
We've talked about earlier with the longer shelf life
Yep, that's right.
than lead acid.
Yep, up to 20 years as opposed to 3 years. Okay. What about temperature? What effect does temperature have on the NiCads?
Probably the opposite of lead acid, so probably less impact.
Yeah, you're right. It's less affected by temperature extremes. So it is the best available technology. Temperature extremes, low risk of application failure, and it can have a lower total life cycle cost over 20 years. You know, you think of those lead acid batteries being replaced every 2 to 3 years, and the cost of those versus the one-time shot of the NiCad battery. So under some circumstances, the cost can actually be lower. With many standby generator sets, the total life cycle cost is not of concern. It's got to meet the spec, it's got to be cheap. Okay, disadvantages. One obvious one.
Cost.
Yeah, that's right. These things can cost up to 10 times that of a lead acid. So they are more expensive. A couple of other things which I haven't really mentioned, so I'll just bring them up. You can special order them. You can't go and pick one up at your local auto parts store. You got to order it specially, and it has to be commissioned on site. It's going to be set up properly with the charging system set up properly. So there's extra cost involved there. Replacement cells are not readily available. They're not as easy to dispose of, and they do have a higher capital cost. Higher. So, you know, you come to the question of where would you use, why would you spend the extra money on the NiCad battery? And I'll answer that for you, because there are a number of places where you need absolutely high reliability. Failure is not an option. Think of hospitals. Think of healthcare facilities where life depends on that generator set starting up. Think of data centers. The cost of a power failure at a data center is absolutely incredible. So what they do at data centers is they duplicate everything. You need 1,000 kW generator set, we'll put 2 of them in there. We'll have 2 independent means of starting each generator set if we can do that. You know, they don't care about the cost because it's insignificant compared with the cost of a power failure. So those are a few places where you definitely put a NiCad battery, where you have extremes of temperature. You know, if you're in Antarctica and the battery isn't up to scratch, you can't just go pick one up or order one and have it delivered to you. So again, failure is not an option. You've got to avoid that. All right, there are some alternatives available. I mean, these are clearly the most popular types of energy storage for starting engines right now, but there are other types as well. Some are new and some are in process of becoming new and available. Here's one. You've already had some discussion on capacitors and what they will do. Well, they can store enough energy in a battery to start an engine, and it will start an engine very quickly. A lot of energy all gets released at one time. The nice thing about this is that there is no chemical action in there. The battery will hold its charge, and it's not going to self-discharge. And these are incredibly light. I used to work for a distributor in Massachusetts. We were at the largest fishing port, commercial fishing port in the country, New Bedford. And we did a lot of work with the commercial fishermen there. And their boats were 70 to 150 feet in length, single screw, but usually nearly always 2 generator sets, because when you're out at sea for a week or so, you can't afford to have a generator failure. So there's always 2 on board. So our business was building the generator sets and maintaining them. A battery manufacturer came to us one time and said, look, you know, you're on these boats all the time. How about you sell them batteries as well? It sounded like a good idea, so let's do that. It took a couple of visits to a boat when we realized it was totally impractical for our mechanics, our technicians, to carry a regular lead acid battery down to the from their vehicle across onto one boat, and then usually the boat that they wanted was about 3 boats out, so they got to step over the sides of the boat, across the deck where there's probably scallop chains and all sorts of other stuff, carrying a heavy battery. So we declined to do that. We wouldn't do it, but had we had this battery, that would have been a different story. So there's some big advantages to this, but they do a very fast start. And here's just an example of how much faster it is. So at this point up here, let's take the lead acid battery. We've got just under 13 volts available. Stationary, then we have an event, and the starting sequence starts. The voltage dips right down, and then it recovers as the engine starts to crank over. And these little blips here are for each cylinder that the engine is cranking over. And then we have the engine starting, and the voltage recovers to a lower level. With the capacitor battery, we've got high voltage to start off with. It dips down not quite as far, and it recovers much quicker. Lithium batteries are now coming to the market. Again, they're lighter. Oh, sorry, I think yeah, okay. And here's another one. 10-year life. Lower emissions during the manufacture. And this is kind of neat. The charger is built right into this battery. And this is one, actually I was asked about this at a webinar a little while ago. I didn't know what the answer was because I hadn't heard of this type of battery. But anyway, a little bit of research, and we found, got some data on it. But they were used on some electric vehicles some years ago. For our work, they are, frankly, they're not very useful. They lose their charge pretty quickly. They're expensive, and we wouldn't recommend it. But the question has come up. So if you run across this, then you'll know that it's probably something you should avoid. There's much better technology out there. Okay, let's move on. So decisions. What are you going to choose? Well, we'll take the lead acid battery as the standard, if you like, and we'll compare everything to it. So we've got 4 other types that we're going to be looking at here. So with the lead acid, we've got standard cost. Temperature is critical. NFPA, that determines what is acceptable and what the specifications should be on generator sets that are used for the safety of life and so forth. Baseline on size. Maintenance does require maintenance and checking fairly frequently. And you can see the others. Okay, the NiCad battery. Cost is much more. Hot and cold is really good. NFPA, it does meet that, as does the lead acid. And part of that specification, I believe, calls for the starting system to have the capability of providing 3 separate starts and with a like a 15-second separation between the start attempts. So those 2 batteries will do that. NiCad batteries are larger to install. They do have a bigger footprint. Do need regular maintenance. Start risk is really low, and 20-year life. Faster crank speed than the lead acid. Super capacity. Price-wise, it's sort of in between the 2. Because there's not a chemical reaction, it has the best hot and cold performance. It is not temperature dependent. Does not meet the present NFPA 110, but there are some changes happening there, so it's a case of watch that space. Size, it's smaller, lighter, doesn't need any maintenance at all. Start risk is very low, and we reckon the life of that is between 8 and 15 years. Fastest cranking RPM. Lithium batteries, and you can see. Okay, so there are your choices. But you're still going to find in most instances that the lead acid battery, preferably the AGM, is going to last better than the flooded type, and it will be acceptable for most applications. Okay.
With regard to the NFPA 110, is it not, so it's not in compliance with that? What would be the reason?
NFPA made a decision many years ago, I guess, that critical facilities have to have total reliability. And that is why they specified this sort of safety margin, I suppose, that they wanted to make sure that the battery would last longer than the first cranking event. So, and most batteries do meet that criteria. So that was the main reason to prove that it was suitable for doing at least 3 starts. And if it wouldn't start after 3 attempts, then the problem is likely the battery. So that was the basic reason that NFPA picked those 2. Now, since they did, technology has changed, as you can see from the last 3 types of battery on that column there. So they didn't even consider these. Now, the battery manufacturers have gone back to NFPA, and I think EGSA may be a part of that as well, and said, look, there is new technology here, and right now you are not allowing any of these newer types of battery to be used on critical generator sets. And there is good reason why they should be accepted in most cases. So that's the status as I understand it right now on the NFPA 110. But really what they're looking for is just the best reliability you can get.
And you were saying that a lot of like data centers use an iCAD. Why wouldn't they use the SuperCap?
Good question. Usually the generator sets in data centers are pretty big, and I'm not sure that they could use the supercapacitor batteries. I don't know how many they would need and how large they can put capacitors. It is possible. I'm just not sure what the answer is, frankly.
Well, thank you very much. That's interesting.
Well, thank you for the question. I will look into that, see if they are used on data centers. Let's make a quick note of that while you're doing further study on that list. Supercaps on data centers.
I asked because we have like 3 data centers
Oh,
in
okay.
our hopper for projects.
Okay. That's a very relevant question for you then. Okay, good. An answer for you. Get back to you. What is your name, sir?
This is Judd Sakamoto, NAVFAC Pacific.
Okay. Okay. Thank you, Jack. Okay, you can read this. Corrosion of the positive plate. That is such a big difference right there. The other thing about the that separator plate is that it was designed to have the same life as the rest of the battery, and that life was considered to be for a vehicle, for a vehicle's operation. So really that particular component was designed for, you know, perhaps 500 hours a year. And we're obviously doing it a lot more than that. So how do we avoid that? Okay, so if you've got a standby generator set and you've got a lead acid battery on it, it is better to schedule a replacement at the most every 3 years, especially if it's a standby generator set. It is better to do that than to risk a failure. So we would strongly recommend a 3-year replacement maximum. Use an AGM battery, better than the flooded type of battery. And the other option is a different type of charger that will charge that battery intermittently, like a vehicle. So that brings us on to the next subject of charging. I love that picture. I have been around horses a little bit, and I can tell by that picture, those horses are not happy with what they're having to do right now. So anyway, charging basics. How does the battery get charged? Well, It gets charged, of course, by a plug-in solid-state battery charger, but this is what we're going to be discussing. So recharging a battery is a fairly simple process. If the battery needs charge and its voltage is less than the source of the battery charger is going to make up that difference. It's going to supply voltage into the battery. It's a little bit like you got a flat tire. You got an air compressor. You plug the air compressor into the or connect the air compressor to the valve on the tire. Now, if the compressor pressure is greater than the pressure in the tire, you're going to get a flow of air into that tire. If it's the same, if you've got the same pressure in the compressor and in the tire, there's not going to be any flow. Well, it's like that with a battery charger as well. If you've got the source greater than the battery, then you're going to get voltage flow. There's a little bit of internal resistance, so that has to be compensated for. That's one of the reasons why there is continuous discharge of the battery at a fairly low level. So with charging the battery, let's take, oops, sorry. Let's say we've had a starting event, so the voltage on the battery has gone down. So the battery charger will sense that, and it's going to do a boost charge. It's going to see that there is quite a lot of voltage that is needed, and it's going to supply that. That's what the battery charger does. It senses the voltage, and it compensates for it, and continues the voltage until the charge in the battery reaches a certain level. Then it's going to go from the boost charge to the float charge. We don't want to overcharge that battery because that's going to cause it to get hot, and that will shorten its life. It turns out that that voltage set on the battery charger is really critical. So this is a number that can be obtained from the battery manufacturer. What rate should we be charging that battery? And in this case here, we've taken the example of 2.8 volts, 2.28 volts per cell. So you multiply that by the amount of cells you've got, and that is the rate at which you should be float charging that battery. You don't want to go higher than that or lower than that, because you're either going to get faster grid corrosion, or you'll get failure of the battery due to salvation, and you'll get lower performance as well, of course. So this is going to shorten the life, and this is going to shorten the performance. Well, that's, as I said, that is critical, and it's usually recommended that that charge rate should be set to about 1% of the voltage that is recommended by the battery manufacturer. So this isn't strictly a plug and play thing, folks. This is something that you need to check when you install a battery charger. Make sure that it's set to the correct voltage. Well, that's well and good, but the temperature is going to change, the ambient temperature. And as that changes, it alters the chemical reaction within that battery. So we have to be careful about the charge rate. So if it's, let's see, if the temperature is cold, the chemical reaction slows down. So we have to increase the charge rate to compensate for that. Does that make sense? The reverse is also true. If the battery is in a hot environment, then that chemical reaction is going to be accelerated. And we have to be careful that we don't overcharge it. Or undercharge it. Now, fortunately, battery chargers have an automatic temperature compensation, so we don't really have to worry about this. But this highlights the fact that you can't just put a regular cheap battery charger on your battery. It's not going to be very satisfactory under different ambient conditions. I'm going to pass by that one because we just discussed that very, very recently. So an option to charging and the regular just boost and float charge is that we can do some intermittent charging and try and mimic what happens in batteries that are used in vehicles. So we go to the boost charge mode after there's been a starting event. And then we drop down to the float charge. And then we go down to a lower float charge. This is just a tiny bit of voltage, and we're going to interrupt that periodically. So it's actually completely shut off. It's resting, if you like. And then every so often, we'll refresh the charge, make sure everything is up to snuff, and we'll continue that process as we go along. So that type of charger is clearly a little more expensive. There's a little more programming that's gone into it. But it is a good option of solving the problem of shortened battery life on the lead acid batteries. So if you're float charging, don't guess the charging rate. Set it correctly. And you've got to have a battery charger that is compensating for the change of temperature. Got to do that. Now, here's an interesting situation. We got a generator set here in the snow, and we got an automatic temperature compensation charger on that battery inside there. So what is the problem here? I don't know if anyone will get this. There's a challenge.
The heater in the generator?
Ah, yeah. Let's take it one stage further. What about the heater on the battery?
They'll be at a higher temperature than the exterior conditions.
Absolutely correct. Thank you. Yeah. So the battery charger is seeing maybe 60 degrees inside that enclosure. So it's compensating for that. So it's going to be putting extra charge into the battery. But the battery is at 80 degrees or 70 degrees, whatever it is. And it is toasty warm. That the enclosure could be colder than that. You know, be getting some radiated heat from the engine perhaps, but the temperature there may be as low as 40, 45. So there is a danger that that battery is going to get cooked. It's going to get overcharged, which is going to shorten its life and reduce its reliability. There is a solution to that, of course, as there's to most things. And in this case, we find out that the battery charger is available with a remote temperature probe. So what we can do is plug that into the battery charger, put the other end between the battery heater and the battery itself. Now the battery charger is looking at the actual temperature of that battery, and it will adjust the charge accordingly. So now you have a safe system there. Does that make sense? I see everybody's nodding their head, so thank you. Okay. Okay. Let's look at the crank cycle here, because this brings up some interesting questions that we have to be aware of. So here we've got a stationary engine. Then it suddenly gets a signal. We don't have any RPM. The engine's just sitting there, but we have this breakaway period here where we get a signal, closing contacts on the ATS, the transfer switch, or someone is starting it. So immediately we get a voltage drop during the breakaway period. We're just trying to get the engine rolling here. We have current, locked roadway current. We have a current surge, And then as the engine starts to rotate, we get an increase in RPM. The voltage comes up a little bit and steadies, and the current drops down as there is less resistance to it turning over. So if we get the first firing here, this is all, you know, we just have an engine that's turning over. Now we're firing. So now the RPM starts to climb up slowly at first, and then very rapidly, and it'll reach its 1800 RPM. And the voltage recovers a little bit more, but not the original, and the current flow drops right down. So what happens is if the voltage drops down too low, if we don't get enough voltage, what's going to be the implication there? Well, it's not going to crank so fast, is it? This reminds me that during this period here, with most modern engines, there is no fuel being injected. We know that the engine isn't going to fire until this point. So why put in fuel here? It's not going to light up. There isn't enough temperature in the combustion chamber for it to ignite. So if we do put fuel in here, which is what happens with older engines, then when the engine does start up, all the fuel that's been injected during this period here is going to burn and burn badly, and it's going to result in smoke coming out of the exhaust. So now we have the ability electronically to not turn the injectors on until we reach about 250 RPM. At that point, the engine is likely to fire. We've developed enough heat. We've got the oxygen coming in. So now let's give it the fuel, and it'll light up very cleanly. Now, we're talking about the voltage drop here. And that voltage drop can drop the voltage in half, basically. So that can have an effect on things. So we need that much voltage to crank the engine. That's one part of it. That's one minimum voltage that we need. Here's another one, the electronic control module. I know that I have, and perhaps you have, been in a car where you get in, you put on the ignition, and the dashboard lights up. You might have some interior lights up, but the engine won't turn over. And that's because the ECM doesn't have enough voltage. It's got to have a certain amount of voltage in order for it to work. So that is at risk. You might also have some DC requirements in the switchgear. So when a battery gets sized, it's got to be sized so that this voltage dip is not as low as the minimum requirement for the other items that you've got, depending on the DC. Okay. Sizing a battery. This will be a challenge. An old Fairbanks Morse engine. There's one guy that looks after that engine at that water pump station, and he won't let anyone else touch it. The other two engines are surplus Navy generators taken from submarines after the Second World War. Submarines were scrapped, but the generator sets were kept and donated by the government to municipalities. There's a lot of those around, opposed piston, two-cycle engines. Okay, but what are some of the factors affecting the battery size? And how do you get the battery sized? What recommendations do you get? Well, usually the generator set manufacturer or the engine manufacturer will tell you what size battery you need. they may be supplying it as standard equipment. But if you've got something like that old Fairbanks Morse, or something that's a little bit off the ordinary, you've got to consider the size of the rotating mass that has to be turned. Compression ratio, older engines and natural gas engines will have a lower compression ratio than some of the modern ones. Oil viscosity, many old engines will have a straight, like 30 weight viscosity. That's going to be harder to turn. You may or may not have a block heater. What's the oil temperature going to be? Especially the temperature of the battery. So if there's any application where you've got some odd conditions, you might just want to go back to the battery manufacturer and say, here's what we got. What do you recommend? Put the onus on them to make the recommendation. Oh, just going back. How do you size the battery charger? Ask the charger manufacturer or their representative. Here's what we've got. What do we need? Do we need temperature compensation? Do we need that remote temperature probe? Okay, next, another important part of starting an engine is engine heaters. They need to work, they need to be reliable, they might provide some insulation and heat. So let's take a look at what's available. There we go. Okay, that might not be readily available, but you can get some refreshments from that, as well as heat on the for the engine. So the option for engine heaters, there's basically three types. There's a pad here, which can attach to the underside of the oil pan. These are used typically on small engines, on air-cooled engines, perhaps, where you don't have a water jacket around it. So it's just attached, it's thermostatically controlled. The only problem with this is that it tends to heat the oil in a very small area. So we have to be careful that it doesn't oxidize the oil or start to cook it. This is more common here. Engines have core plugs in the crankcase. This is a part of the manufacturing process. They have holes in there, which in the side of the crankcase where they use to clean out after the casting. So they plug these holes up. You can unplug them and insert a heater like this or this one over here, and it will go into the side of the engine and into the coolant, and again thermostatically controlled, so it'll keep the temperature nice and warm. It just relies on convection. So the hot coolant is obviously going to rise to the up to the cylinder head area, and it'll continually recycle. The best option, especially on larger engines, is this type here. And here we've got an external heater, and we're circulating coolant from the engine through the heater and back into the engine. And here's what it looks like on an engine. And the coolant comes in here, goes through the motor, force through, and comes out this way. So we're taking the coolant and pumping it into the engine. And this happens continuously. Again, thermostatically controlled. It'll shut down when the engine is hot and when the engine is in operation. Any questions on battery heaters? Apart from where to buy the cow. Okay. I've mentioned the duplication and redundancy that is required by data centers and a few other installations as well. What they would like to have is duplication of the starting system. Now, there's not many engines out there that have the capacity of 2 starter motors. Some do, but not many of them. I mean, 2 starter motors would be ideal, because that way you can have 2 completely independent means of starting the engine. If one fails, then the other one will take over. Say you've got 2 starters, 2 batteries, 2 battery chargers, everything together. Now, another option, if you don't have that, is a best battery selector. And what we've got inside here are a pair of diodes and a big heat sink. And this has the ability of finding out which is the strongest battery, and it will pick that battery and allow the current to flow from that battery to the starter motor without allowing this diode here to open up. So it will automatically select which battery is needed. And there's no moving parts, there's no chemistry involved. It's very simple and reasonably expensive. So that's just an option that is popular in critical installations where you need to have 2 independent means of starting a single engine. And there's a lot of useful information that you can get now. We know we can monitor the engine and all its conditions and the generator and all its operational conditions. We can also monitor the condition of the battery as well. There's various types of battery monitor that are available, and they can give you an alert if the battery voltage drops down or if it's too hot or needs some attention. What kind of batteries are we looking at here, folks? Can you tell me? These are individual battery cells.
The flooded type that you use in ops.
Close. The giveaway here, though, is a connection between the cells, which is external. So these would be DiCAD. These are your NiCad batteries. Okay, just a quick review here. These are charged 500, 600 hours a year. Genset batteries 8760. Validation by the manufacturer. Done on vehicles, not on genset systems. Starting components on gensets can be chosen by almost anybody. And we are skeptical of some of the consulting and specifying engineers, frankly, because not all of them keep themselves up to date on new technologies. Battery heaters, we've got to be aware of if they're there, because they can cause problems if there is not a temperature probe in there telling the battery charger what to do. Some of the lowest cost components cause 80% of the starting problems. And this is what you can, up here is what you can see on a vehicle sometimes. You get warning. You do not get warning on the average vehicle. That's the most critical one right there. We want your generators to be ready to start anytime when they're needed. They do need some maintenance. This is fairly obvious, but I'd like to just mention it anyway. Don't take a risk with uninsulated tools if you're around a battery. It can get very exciting for a very short period of time. It can have major effects. So if you're going to inspect an installation, take a good look at the battery, check the electrolyte level, check the specific gravity. If the specific gravity is getting down towards 1, that means that that electrolyte is pretty well spent. When it gets down to 1, then it's much the same as just water. And we know what happens to water when you get down to 32 degrees Fahrenheit. It's going to freeze. The whole battery will freeze. And at that point, the electrolyte is totally useless and it will not recover, and it will not start the next time. So check specific gravity. Make sure that make sure the terminals don't look like that on the lower right. Cell temperatures, that's a wise thing to do, particularly with the NiCad batteries. You can check each cell individually and make sure that one isn't any hotter than the rest of them. And that I mentioned. Maintain good records. This is something that is particularly important in the commercial field, because you may have a case, and I've seen this happen, where a generator set failed to start during a utility failure. The facility manager was absolutely furious, pointing out that our tech had been out there 3 months earlier. We had the records which he had signed off on, where we had recommended a battery replacement, and he chose not to. So the onus was on him. Sorry it happened, but you know, it was your decision.
What happened in that photo on the bottom right?
Bottom right, a lot of oxidation over the terminals. That is all, what is it, acid and stuff, oxidized acid, I think is what it is. Obviously, it hadn't been looked at for a long time. I got some important takeaways for you, some summaries of some of the important stuff, and you might want to review this when you go over the presentation at some point in the future. Now, there's one other thing which I just got a couple of minutes here, and we're in good shape time-wise, so we've done well, I think. Guys, I would strongly recommend that you stay up to date with what's going on in the world on power generation. You guys are in a really good position for the future, because you're in an industry that has a lot of demand for people. When you leave your present positions, if you're looking for a job in the commercial area, you won't have any difficulty finding a job. But we do recommend, or I certainly recommend, that you see what's going on. I get a lot of information out of these two. Diesel Progress magazine, you can get a free subscription to that magazine. You can get weekly updates on what is going on engines, on generator sets, and a bunch of other stuff that uses diesel engines that may not be relevant to what we're doing. But advances on truck engines, vehicle engines, construction equipment does have some relevance, because the engines we use in power generation originate in those industries. There's no manufacturer that designed and built a gen drive engine just for our small little industry by comparison to the on-road and off-road vehicles. Powerline magazine frequently has some really good articles on different installations, all about generator sets. And here's something I read about fairly recently in my own state of North Carolina. Camp Lejeune, they lost power from the utility for a full week. No power on the base apart from a few buildings. So the camp went just about black, which was a really serious situation. What they're doing now, and probably well into it, is they've decided to go to a microgrid system using generator sets, wind, and solar. They're combining resources with Duke Energy, who's helping them with this. But this will basically take them off the grid. And there are a number of camps, I know certainly in the Army, I'm not sure about the Navy, but a lot of military bases want to separate themselves from the grid. It's just not reliable. And most of our utility power comes from power stations. Some of it is coming from renewables. But we have the power stations, different energy source. Power stations, basically they boil a kettle, take the steam and run a steam turbine with it, which in turn powers a generator. And from there it goes to the distribution system. The problem that we have as a nation, frankly, is that the distribution system has evolved over a century without any planning for the whole system. You know, when the electrification of the country started, there were small utility companies that were just supplying their own area, their own region. And after a little bit of time, these utility companies started to combine, and now we have about 3 different power generation systems across the country: the East, West, and Texas. And the system is basically fairly old. It is prone to failure, and now we're finding, which is really disturbing, that people are going out there with the view of sabotaging them. It doesn't take much to destroy a fairly large transformer. If that happens, the whole area goes black. Now, the solution, of course, is on-site power generation, where we generate our own power. So the news is fairly good for the power generation industry. The truth is, of course, that you can't usually generate power for the same cost as you can buy power from the utility company. But if reliability and independence is important, then that's the way to go. Okay, we're just about there. I'll just see if this will go. It won't, so I'll move on. So it is exactly 4 o'clock. And I can tell you that if you have any questions, I will respond to you. And I'll try and do it as quickly as I have with the other questions that have come up. But let me know if there's anything I can help you with, either on power generation or on starting systems and prime movers.